AC equivalent circuit that we derived in part 37 of this lecture series. For NMOS device, we have a very similar AC equivalent circuit and a small signal model for a Pmos transistor. You see these in figure 8A, you have a common source circuit with a Pmos transistor. The only difference between this configuration and an NMOS device is the reversal of current. Okay, the current direction over here is out of the drain. Okay, it's out of the drain, and the voltage polarities are reversed. The voltage polarities are as such that okay, you're still taking the output from the drain, but the source is at the higher potential with respect to drain. So the source is at higher potential with respect to drain, and the source is tied up to VDD, which is the DC biasing. Okay, I mean, if you compare the circuit, this DC circuit with the NMOS device, over here you see the direction of the current is into the drain. Okay, and you have VDS over here. You're still taking the output from the drain, but the direction of the current over here that's going into the drain and out of the source. That's the conventional way of giving the current direction for an NMOS device, and the voltage polarity is VDS. Okay. Similarly, you have VGS, where the gate is at positive potential and source is at the lower potential. So in this device, you see the VDD is connected to the drain. Therefore, drain is at higher potential with respect to source. So this is VDS. Okay, that's the output. But over here, you have source, which is at the higher potential with respect to drain. So first of all, the voltage polarities as compared to the NMOS device are reversed. Similarly, you have VSG, which means the source is at higher potential than the gate. You don't have VGS. Okay. So other than that, the direction of currents and the polarities, there's no difference between the AC equivalent. So for example, this has both the DC and AC parts. So if you have to derive the AC equivalence, what you do is you kill all the DC sources. Okay, so you see this is a common source circuit, because if you remove this VDD, you make this ground, an AC equivalent circuit. Then this becomes an AC ground. Okay, which means that the source is common to both the input and the output. So over here you see the source has been grounded. This becomes an AC ground over here. The source is AC grounded, and then you kill this VGG source as well, the DC source. Okay, so you're left with the AC equivalent circuit, right? And VI small v small I is the AC signal applied at the gate. Okay, and apart from that, you have this reverse voltage polarities compared to NMOS, and this is basically the AC equivalent circuit. The only thing you need to plug in over here is the small signal model for the transistor, and it turns out the small signal model for the Pmos device is very similar to the NMOS, except for the reverse current directions. Okay, the current direction over here, you see ID is coming out of the drain. Okay, it's out of the drain. Now if you compare this over here, in this NMOS device, it was into the drain. Okay, the current direction is into the drain. So the current, basically the current polarity ID is changed. Otherwise, ID, since when the transistor is operating as a linear amplifier, this is the transconductance amplifier. Okay, so it is still given by I, where the input is VGS and the output is ID. So with the transconductance gain, the input is still the voltage and the output is the current, with the exception that in Pmos device the direction of current is reversed. Okay, so that's all. So what you do is you substitute for the small signal model in this circuit, and you have the full-blown AC equivalence. So okay, now figure 8A shows the circuit containing the P-channel Mosfet device. Note that the power supply VDD is connected to the source, so the source is at higher potential. Also note that the change in the current directions and the voltage polarities compared to the circuit containing NMOS. Now figure 8B shows the AC equivalent circuit with DC voltages source replaced by AC short circuits, and all the currents and voltages shown in the time varying components. In figure 8B, the transistor can be replaced by the equivalent circuit. In figure 9, this equivalent circuit of P-channel MOSFET is the same as that of the N-channel device, except that the current direction and voltage polarities are reversed. So let's have a look at the figure 9. That's a small signal equivalent circuit model. Once again, you have this transconductance gain. The input is the voltage. This is not VGS, this is VSC, because S is at the higher potential than gate. Okay, so therefore you have this is negative and then this is positive. Okay, which means that if you consider an input voltage VI over here at the gate with plus and minus, then VI and VSG are related as such. Okay, so there's a negative sign coming up over here. So it means the voltage polarity is reversed. Okay, so this is the first thing. The second thing is that the direction of the current, you note, is different. Okay, for PMOS device. For NMOS, it was the other way around. It was from it's from right to left. So the also you see the direction of this dependent source is like this. Okay, so over here, if I change the polarity of the input source, or over here you change this to plus and minus, it becomes VGS, then the direction of current has to be reversed. Okay, so what I mean is, if this becomes plus, if this becomes negative, the input voltage as such, the current direction has to reverse itself, so therefore it becomes an NMOS, small signal equivalent circuit model. Okay, but again, apart from the reversal of voltages and the currents directions, you don't have any other difference in the model. Okay, it's still a transconductance amplifier with the input, but it's the voltage, and the output is the current. Okay, then similarly you have the source which is at the higher potential than drain, so the output is VST. So small signal equivalent circuit model for p-channel Mosfet amplifier is shown in figure 10. So over here you have the small signal equivalent circuit model for the common source amplifier with Pmos transistor model. So in this model, just you have what we have done is the VI is your minus VSC, you can see it from here, and then you have this small signal model of the transistor consisting of a dependent current source and output finite resistance R0, okay, which is there due to the channel width modulation of the channel due to VDS. Okay, so we have derived this in the last video. R0 is due to this modulation parameter lambda. Okay, because the current is in saturation. As a linear amplifier, you have to bias the transistor in saturation. So if you take the gradient of this curve, ID versus VDS, take the inverse, so it becomes ohms. Okay, so this is your forward resistance, which has to be accounted for in the small signal model. Okay, and note that this small signal output resistance of MOSFET device is dependent on the Q parameters, that is the IDQ. Okay, that's the Q-cent DC current 1/11 IDQ. So it's still there. Okay, so apart from the direction of current and the voltage, you have a very similar model, small signal model for the PMOS device as well. So again, the output voltage is given by GM VSC, and then you have this R0 in parallel with the RD. Okay, and if since VSC is minus VI, so it means that the voltage gain still consists of the phase reversal. There's a negative sign over here. Okay, which means in both PMOS and NMOS device, the output voltage and the input voltage are 180-degree phases apart. You see, so the things to notice over here are the voltage gains are similar. Okay, so for PMOS device, for NMOS device, what we had earlier, we had the voltage gain. We have a very similar expression for the voltage gain, in fact. And this voltage gain was given as, so this is minus V0 is basically minus GM ID. So ID is given by VGS RD. Okay, if you recall it from here, small signal equations that we have. So it's minus GM VGS RD. But this did not have this R0 in parallel. Okay, so in small signal model, you have this parallel R0. Okay, so the output resistance is R0. But however, since we are considering very low frequency signal at the input, therefore the gate capacitance over here, the gate capacitance is negligible. It's open circuit, okay? or the resistance is infinite. The input resistance is infinite, so you don't see any input resistance with the gate. Okay, it's low frequency signal. But at the output, due to the channel width modulation parameter lambda in actual MOSFETs, you don't have this plateau region. It varies like this. Therefore, you need to consider the gradient. So you have this R0, the finite resistance given by partial ID by partial VDS. Okay. So The expression for NMOS device and PMOS device are very similar. That's the first thing. There's a phase reversal, there's a negative sign. Okay, so if you consider it over here, again, you have the same voltage output, and then you have the same voltage 180-degree phase shift reversal. So the input and output, you have 180-degree phase difference. So this expression for the small signal voltage gain P-channel Mosfet amplifier is exactly the same as that for N-channel Mosfet. The negative sign indicates 180-degree phase reversal that exists between output and input signals for both PMOS and NMOS devices. Okay, and these both configurations that we consider are common source configurations. Okay, so in both configurations you have 180-degree phase reversal between input and output. So we may note that if the polarity of the small signal gate to state source voltage is reversed, the small signal drain current direction is reversed, this change in polarity is shown in figure 11. Now you see this is what we have considered for PMOS device. Okay, this is a small signal equivalent circuit model for P-channel MOSFET, showing the conventional voltage polarities and the current directions. Now if you change the polarity, this is VGS, then so gate becomes the gate is at a higher potential with respect to source, and so VI becomes equal to VGS. Okay, it's not minus VGS. Then the direction of the current is reversed. So this model is very similar to what we have seen. This is exactly like an NMOS device connected in common source configuration. So this small signal model corresponds to an NMOS device in common source configuration. But we are going to stick to this model, which is shown in figure 11A, because this still holds the voltage polarities and the current directions which are associated with the PMOS device. Okay, but just for illustration, in part B, the case is illustrated when the voltage polarity and the current direction are reversed. So the small signal model of PMOS device becomes very similar or equal to your NMOS device. Okay. All right.